Okay, let's go ahead and start. Welcome all to the AI seminar series by Matrix. This is the second semester we are hosting this. I am Dirisha Kurtipudi, the director of the Matrix. And today I'm honored to introduce Dr. Raymond Ptucha, who is a dear friend and who has recently started as a computational display technology leader in the visual experience group at Apple, where he's responsible for developing machine learning products in display. Prior to that, he was an associate professor in computer engineering and the director of machine intelligence laboratory at RIT. Ray has almost 20 years of experience as a computer vision, machine learning, and robotics researcher. More importantly, Ray is extremely passionate about engaging students in different machine learning and deep learning activities. He has been an active member of the local IEEE chapter and the FIRST Robotics organization. And he has also done significant research in the computer vision space before joining RIT, where he was a research scientist at Eastman Kodak. And he has patented over 33 technologies in computational imaging algorithms. So Ray also has received the NSF Graduate Research Fellowship in 2010 and has also earned the Best RIT Doctoral Dissertation Award in 2014. So there's quite a few accomplishments under the sleeve, but what really stands out with Ray is his passion for teaching and his excitement to engage with students in this space. So it's an honor to have him start off or kickstart our AI seminar series for the spring semester. Ray, the screen is yours.
Thank you so much. Thanks for the great introduction, Dirisha. Okay, so what we're going to do is we're going to take a little story about deep learning. I love deep learning. I love technology, and we are so lucky to be alive where we are. You know, we can pack billions of transistors on a single chip. We can fly airlines routinely at 550 miles per hour, construct awesome buildings like you see here in Dubai. Information, big data is just all over the place, and this is the fuel which is enabling big data. So let's just say I love deep learning, and deep learning networks are awesome, but they have some limitations. And so what I'm going to talk about is some of the attacks that we've done to try to tackle some of those limitations. And I'll start out first by handling this particular situation where neural networks are forced to make a decision when you give it an input. And sometimes that's good, sometimes that's bad. And just so we're all on the same page, let me just do a 1-minute synopsis on how a typical neural network works, and that maybe will help us answer some questions about what do you mean by it's forced to make a decision. So what we have over here is we have a typical multi-layer perceptron neural network. We have some inputs over here, we have 2 hidden layers, and we got some outputs. So typically, let's take a vision example because it's easy to see and relate to. So in this particular case, we're going to do a discrete classification, where we take an image and we're going to assign it of one of these output classes. So these red boxes now are output classes. If you're going to classify some unforeseen image as, say, a person, a car, a boat, a motorcycle, a cat, or a dog, there could be 100 classes over here, and they're predetermined in advance. Okay, so we have an image as an input, and let's do a toy example where the images are maybe 20 by 20 pixels. So what you do is you string all those pixels together into one long vector. So if it's 20 by 20, it'll be a vector of 400 long, and these would actually be the code values of each of those 400 pixels. And so what happens is in this first layer, each of these hidden neurons is a linear combination of each of those 400 input pixels. And so this particular neuron has got its own unique combination of all these input pixels. The second one has got a different unique combination of all those input pixels. The third one's got a different unique combination, and so on. And so let's say there could be a couple hundred of these neurons over here. Then we repeat that process in the next hidden layer. Now this neuron is a linear combination of all these hidden neurons. This neuron's a different linear combination of all those hidden neurons, and so on. And then when we get to the last layer, what we want is, when it's a picture of a person, we only want the output node assigned to a person to light up, and we want the other ones to be 0. So for example, when we give it a picture of a person, we want to see a 0 over here, a 0 over here, a 1, and everybody else being a 0. Now, of course, when you first start with a neural network, these weights, and there could be millions or hundreds of millions of these, they're just randomly set. So when I input an image of a person, that 400 long vector of code values, what are the odds that I'm going to get 0, 0, 1, everybody else zeros? It's not going to happen. So there's going to be some error with the ground truth. And so in this case, every input image during training has got a corresponding ground truth vector, which would be in this case a 0, 0, 1, everybody else is zeros. We take the errors that we're seeing, whatever we got, which wasn't 0, 0, 1, all zeros, we take those errors and we do something called back propagation to update all the weights one layer at a time, such that then if I were to pass that same image in a second time, I would be closer to getting 0, 0, 1, all zeros. And then I'll take a second image. This time it's a picture of a car, and I'll do the same thing. I'll pass it through all the layers. And with a car, I'm hoping to get a 1, all zeros, but I'm not gonna. So I'm gonna have an error over here. Whatever that error is, I use that back propagation process to update all the weights. And then I'll do another image. This is a picture of a person that's hard to see. And so for a person, we want 0, 0, 1, all zeros. And we repeat that process for many, many, many images. And there could be a million images that I use to train this network. When I'm done, I repeat the process. Each time I go through all those images is called an epoch, and I may do a couple of thousand epochs in some particular cases. Now, the idea is that when this thing is trained, I could take a picture, say, of my dog on my couch, which it's never seen before. And when I pass in a picture of my dog on my couch, lo and behold, I get something very similar to as all zeros followed by a 1 at the very end. And that's sort of like the beauty of neural networks. But then I ask you, what happens when I take a picture of something like this? Wait a minute, this is an astronomy image. This happens to be the Wizard Nebula, NGC 7380. What's it going to do? Which one of these nodes is going to light up? And I don't know. It was never trained on this, but yet one of them is, it's going to have to give an answer, and what answer should it give? And so this is the first weakness of neural networks. And so if we take a scenario like, how about medical imaging? And let's take an example of dermatology. Doctor-assisted diagnosis is very common today. It's very hard for doctors to know, the hundreds of different lesions that are out there. So taking a picture and giving some aided advice to the doctor is usually a good thing. So the neural network may be trained for a couple of hundred different lesions. But what happens when you give it something unexpected? Well, it's still going to say, hey, you're one of those, it's going to force it to be one of those 100 different lesions, whether it's right or not. I mean, you could have a confidence, of course, but still it's going to confuse the dermatologist. For example, this image of a dress, it's giving a 98.56 confidence of this disseminated actinic porokeratosis. Same thing with this particular image, it's giving a 95.15% confidence of dysplastic nevus. So this is very confusing. So what we'd like to do is we'd like to add a better measure of uncertainty into the neural network, something better than the simple confidence you would get from a softmax. And so the idea is well, why not just use an ensemble of networks and then they vote on the answer? And that's generally a good idea. If you're ever entering a competition, I strongly advise you do something like that. Well, maybe we could even modify the neural network to give, every time you give it one input, and this is during inference, after it's trained, you give it one input, and maybe it gives you a whole ensemble of outputs, that one network. That would be really cool. Well, somehow, if you can get a distribution of outputs, maybe then you can take that distribution and do some, handcrafted, human-engineered features on those statistics, or maybe you just pass them all into a machine. Depending upon what you do, you could pass them into another neural network, which would learn, was this a realistic image, or was this, some irrelevant image which I was never trained on for that particular class? Now, you definitely could learn an ensemble of neural networks, but training is probably the longest part of a neural network. It could take several days or several weeks on some of these neural networks to train them. So now you're saying you have to learn an ensemble of them, say 100 of those? Oh my God. So now it takes 100 times longer to train. So instead, there are other options. What we can do is we can change this vanilla network to something called a Bayesian neural network. And so the idea is instead of just learning a single weight, say for one of your particular layers, we're going to learn a distribution or parameters of a distribution, like a mu and a sigma. So the point is if I learn a mu, instead of just learning a single weight, I'll learn a mu and a sigma. Every time I pass in an image, when I get to that particular layer, now I'm going to sample from that distribution to get, to pass on to the next layer after that. And that means since I'm sampling randomly from that distribution, from that mu and sigma, every time I pass in an image, I'll get a different answer. Similar, we can use dropout. So dropout during training is when you randomly drop some weight connections. Well, wait a minute, why not do that during inference? Why not randomly drop some connections during inference? And we call that stochastic dropout. So both of these are clever ways of modifying the neural network such that when you give it one input, you get a whole distribution of outputs. And so the idea is that when you have some sort of uncertain input, when you look at that distribution, so for example, over here, I think there's 80 some odd classes over here. If it was very certain about a class, you would get one peak at that particular class and everybody else will be flatlined. In this particular case, it's not sure, is that class 5 or 11 or 22, or is it 39 or is it 49? It's just not sure. And so this variability here, this is sort of like the uncertainty. This is a really good metric to tell you that that particular image that somebody just passed in has nothing to do with dermatology. It's that, that wizard nebula, that astronomy picture that was passed in. All right. So what can we do with this? So we'll say we have a C by N prediction matrix. So we do this N times. Each time we do it, we have C classes. So let's assume this is 80 classes and N you could say is 100 or something like that. So really I have an 80 by 100 matrix, which I can extract some features from. And I can do that hand design or the machine learned. So for example, humans are great. We've been doing statistics on data for hundreds of years, and we know all these really cool measures, entropy, different types of areas under the curve, KLB, Jensen-Shannon divergence. There's so many things we can do to measure sort of the stochasticness or measures of uncertainty of these particular curves. So let's just use them all, all right, not all of them, but, all the popular ones let's use, and we're going to see if we can pass those into a network. And then what we'll do is, so let's say if if our matrix was 80 by 100, and I extracted 14 of those hand design features, now I'll do a 14 plus C output over here. This C, this is that 80 classes that we had there. That's sort of like the median distribution from each of those 100 measurements I did. And the 14 is the statistics which we collected from those 100 different measurements. So what we're going to do is we're going to take that 14 plus C and pass it into yet another neural network. And the only job of this neural network is to say, hey, it's got two outputs. Was that a known sample or is that garbage? Some irrelevant image which has nothing to do with what this neural network is trained on. Okay. Alternatively, you could say, hey, skip that handcrafted feature thing. Folks who know me, I'm not a big fan of handcrafted features. Sometimes they work really great, but often if you leave it up to the machine to discover what those features are, usually the machine does a better job. And so in this particular case, let's leave it up to the machine. What we're going to do is we're going to take that whole C by N matrix and pass that into the neural network and ultimately make the same decision at the end. Either I know this is a good sample or this is a garbage sample. Has nothing to do with dermatology. And so to cut to the chase, because we're short on time, both of these methods work really well. The machine-generated one gave slightly better results than the handcrafted, but they're both pretty good. And as we were doing more and more experiments, doing the final ablation analysis for the paper, we started shrinking that number n to see what would happen. And lo and behold, as we were shrinking the number n, it's like, wow, these things are still working pretty good. And then we did one extreme test, which was, hey, just take that logits vector out of the softmax, pass that into one of those binary decision things, and lo and behold, that worked almost as good as both of those really complicated techniques. So I tell folks, if you need an uncertainty detector, just add one more set of nodes in your neural network for the relevant, irrelevant, which will take the output of your softmax. And it generally works very well. Okay, so the other issue we have is that these deep neural networks, they could have millions and millions of weights. You know, how many training samples do you think you need if your neural network has 100 million weights? It's like, wow, I need a lot of training samples. And so this is generally something that we have to ponder and say, well, what are we going to do about that? And so let's take another use case. In this case, let's take speech recognition. And I'd like to use an example of Seneca, which is a Native American Indian language spoken in Western New York, you know, where I am right now. And it's a dying language. It's, you know, there's less than 50 native speakers left. And what this means is that that culture, that heritage is dying. And so now there's a resurgence trying to train more people. And so now we have a few hundred second language speakers, but still those native speakers who have all those great stories and all those myths and all the Bible stories and the heritage passed on from generation to generation, it's being lost. Matter of fact, another interesting tidbit about Seneca is that they didn't even have a written version of the language until the 1980s. So this is very important that we take these stories which have been passed down from generation and preserve them forever. So we want to do something like speech recognition, but this is what we call a low resource task because there's very few minutes of transcripts of Seneca. It takes roughly 10 to 60x to 1 ratio. So if you're transcribing Seneca, let's say you're a native Seneca speaker and you're listening to something and then you're typing in the computer exactly what it said, for every 1 minute, it would take you anywhere from 6 minutes to dozens of minutes to transcribe any 1 minute of listening to audio. And so at high level, speech recognition is no different than vision. And matter of fact, one of the common ways of doing speech recognition is forming these things called the spectrograms, which has got the time. So over any unit in time, what is the frequency content? And I'm just showing a couple of variations, of popular variations of those. And then you can pass those into your neural network. And you have your choice. You can treat this as an image, or you could do some sort of recurrent thing where you just take vertical slices, one vertical slice at a time, passing into your recurrent neural network. The idea is you take a sound bite, pass it in, you extract these features, you pass that into your neural network, and then generally we have a language model which cleans things up. For example, you know, if I say, you know, what is the next word at the end of the blank? And, you know, going by statistics using, you know, n-grams of words and stuff like that, statistically, it probably would be sentence would be the last word there. So this does a lot of cleaning up, which, you know, sometimes there's some noise from these acoustic models. But in the end, you get the transcription of whatever was being said. And then we use rate measurements of like word error rate or character error rate to see how well it did. So, all right, so we need more data. This is a resource constrained language. So how are we gonna get more data? So we go to our buddy data augmentation. So what can we do for data augmentation for speech? Well, we can change the speed, we can change the pitch, you can add various amounts of noise to that particular sample. You can even do something like, well, so what we're gonna do is voice conversion. And in particular, we're going to use non-parallel voice conversion, which means we're going to go from a male speaker to a female speaker, or from a young person to an old person, just in general. And so how do we do something like that? So we use what we call StarGAN. This is modeled after CycleGAN. The idea is you have speaker A, a whole bunch of utterances from speaker A, and then you have a whole bunch of utterances from speaker B. So the idea is in this particular network, we're going to start out with, a random, you grab a random utterance of speaker A, and we're going to pass it through a generator. The job of this generator, it's a neural network, it's to transform from speaker A to speaker B. Then we're going to take the output from this generator and first of all, pass it into what we call a discriminator. And so this particular neural network, again, it says, hey, was that a real or was that a fake spectrogram? That's his only job in life, is to tell if this was real or fake. And so during training, sometimes we're going to give it a real spectrogram from B, and sometimes we're going to give it a generator one. And so this guy is going to be an expert at determining if this is real or fake, which is going to force this one to do a really, because they're going to battle it out. They both want to win this particular battle over here. And so this one's going to get better and better at making realistic looking spectrograms. And then the second classifier says, oh, by the way, it also needs to be classified as B, not as A. So forcing it, so is this a realistic spectrogram? And oh, by the way, is it a spectrogram from speaker B? Now, CycleGAN, it became famous. It came out a couple of years ago and said, hey, we're going to put this loop back in there. We're going to put a second generator, which is going to go B back to A. And then we're going to do the reconstruction, the difference between these guys. And we're going to try to minimize that reconstruction error. And so really what we have here is we have two generators and two, say, detectors, classifiers over here. And then we also have a flip side where we're going from B to A and then going from A back to B hat and then doing the reconstructed. But these generators, there's always going to be one A to B generator and there's always going to be one B to A generator, whether you have this or the mirror image. And they're all trained simultaneously and it does a great job, and that's what we use. All right, anyway, so let's get back to the resource constraint. So we're going to first create a baseline architecture using something called deep speech, made famous by Baidu. And so initially came out in 2014. We're using a version from Mozilla from maybe 2 years ago it came out. In any case, in this particular architecture, it is a recurrent neural network. So it's going to take, so you have this spectrogram, this is the time over here, and this is the frequency content over here. So if somebody keeps on speaking for 100 hours, this thing keeps on going on for 100 hours in time. If somebody only speaks for a second, this is only 1 second long. So the idea is you're going to take an utterance of a certain length, and this is the frequency at each point in time. You take a window and you pass it into this neural network, and then you're going to output a sequence of characters. So each time slice is going to kick out a character, and then it slides over. And we allow blanks, which is like a skip, because sometimes I could say a word really slowly, or I could say it really fast. And so either way, you got to get the right answer. And so we have to handle these things of repeated characters and blanks and stuff like that. But these are all solved problems today. Anyway, so this particular network, it was trained on 7,000 hours for English, and it works pretty good. Okay, so that's why it's famous, because it works so well. What do we have in Seneca? We only have 10 hours of data. Oh my God! So how are we going to train all these weights with so little data? In any case, so here's what we did. So starting with that deep speech architecture. Initially, it's a random initialize, but what we're going to do is we're going to say, hey, we're going to train it with 7,000 hours, say on English, to initialize all these weights to a good form. And we call that transfer learning. So before we even start doing any training on Seneca, we have the weights in somewhat of a reasonable position, at least for speech recognition, well, at least for English speech recognition. But what we want to do is now we want to fine tune that on Seneca. And so initially what we do is when we do the fine tuning, we take this heavily augmented data set to try to get these weights working on Seneca. They started working on English, now we want to get them to work on Seneca. And then we do a third phase where we say, hey, just do very little or no augmentation and fine tune it in this third stage. And when we do learning like that, we're able to take the low resource data set only goes used for training in that final fine-tune stage. But for example, that voice conversion or the speed or the pitch or the noise data augmentation, all that stuff is heavily used in this second stage over here. And when we do that, we get great results. And so if we take a look at this chart over here, what we see is that if we just do augmentation alone, it's not that good, because augmentation can be really noisy data. I'm just changing the pitch randomly. I'm adding noise randomly. So if I fine tune the network with that, it's going to make it worse. But if I take the heavily augmented data and then pass that into a third stage where I fine tune the neural network, all of a sudden I'm getting better results. And then if we use the StarGAN VC, this is that voice conversion, wow, we even get better results. And so for those of you who love deep learning, you may say, okay, augmentation is great. Transfer learning is great. What about self-supervision for initializing those weights? And so we've done many experiments with self-supervision. And to date, we haven't been able to beat this particular strategy, but I love self-supervision too. We could talk offline more about that. And then I'm going to skip over these next couple of slides. This is some improved architectures that we came up with for better speech recognition using that same paradigm where we first do the transfer learning, then the heavy augmentation, and then the third stage, the fine tuning. And in general, when we do this and all these variations, it keeps on getting better and better and better. And irregardless of the number of training minutes that you have, remember, English has 7,000 way out over here. We started with Seneca with only 10 hours, and we tried it with as few as just 1 hour over here. We even did it on other languages just to show it's not just for Seneca. All right, and so this brings me to the third part of the talk. And so now we have this scenario where neural networks really have transformed, science and technology and our lives the way we know it, and really are doing everything they can to improve the quality of life. This next generation, which is growing up, is going to have probably the biggest boost in quality of life of any other prior generation in all of mankind. We're so lucky, it's so awesome. But anyway, so the current neural networks that we described so far, geez, they only work on these gridded structures. But most of the world's scientific problems aren't gridded. If you take something like weather, you have a variable changing, cities, different distances. Sometimes they're close to one another, sometimes they're far, sometimes they're downstream from the trade winds, sometimes they're not. What about chemical structures? There is no unique gridded to a chemical structure. And then we think, well, everything that we talked about so far is predicated on either those multi-layer perceptrons or CNNs, which are convolutional neural networks, the convolution operation. And when you have a gridded structure like an image or a spectrogram, it's very easy to do one of those convolution operations. Replace this pixel with what? Well, a linear combination of itself and its 8 nearest neighbors, and so on. Well, how would you do a convolution on a generic graph? Here's a chemical structure. Here's a network, a plot of a network graph. Well, okay, so I could replace this vertex with the linear combination of itself and its 4 nearest neighbors. All right, who do I go to next? Over here is very obvious. I start in the upper left-hand corner, and I step through everybody in the first row, then step through everybody in the bottom row, and so on. Over here, we don't even start. I don't know. This one's got itself and its 4 nearest neighbors. This one's got itself and its 2 nearest neighbors. This one doesn't have any neighbors at all. So it's a difficult problem. What about pooling? The way we've done the images in deep neural networks, we have these levels of abstract hierarchy, and separating each level is like a pooling operation, to reduce the image or the complexity. How do we do that? It's not so obvious how do you do that with a graph. And at the end of these convolutional neural networks, we generally take our low resolution image, and there's so many layers, and we connect it to a fully connected layer. That means that this particular node is a linear combination of all the, say, pixels in this layer, plus all the pixels in the second layer, plus all the linear combination of all the pixels in the third layer, and so on. It needs to know in advance how many inputs it has. Same thing with this second entry, the third entry. They need to know exactly what's coming in. And when we talk about graphs, there's all kinds of crazy variation. So, we have some problems to deal with. So we have our gridded structures, which are great for convolutional neural networks. And then we have the real world, which is not gridded. We have homogeneous samples, which, a fair amount of the world is homogeneous, but honestly, most of the world is just heterogeneous. What I mean by that is that the number of samples can change, the connections can change. No two chemical compounds have the same number of vertices or the same number of edges. So that would be a classic example of heterogeneous connections. So there's several ways of attacking this. Early ways we're doing these spatial approaches, using these building blocks, or doing crazy padding or cropping of the data. Then there were spectral approaches, just like in the, if you want to do image processing, you can go into the DFT, into the Fourier domain, and do filtering in there. And you can do the same thing over here. It's got the same weaknesses and disadvantages as imaging, but it works. But so can we get something that would work in the spatial domain so we don't have to go into the frequency domain? And so here's just a list of common methods, very hot topic, started a couple of years ago. And the one I like to tout is this thing called GraphCNN, which RIT released in 2017, and now there's been several versions since then. But the idea is you have a generic unstructured graph. You define convolution operations and pooling operations and convolution operations and pooling, and now you have this abstract hierarchy of the graph as you go deeper and deeper into the network. So it's a very powerful concept. I just want to take a couple of minutes to explain how it works. So for example, let's take a look at, so here's a toy example. The image itself is only 2 by 2. So I'm sorry, 2 by 2 filter with a 4 by 4 image. So this is the filter, 2 by 2 filter, and a 4 by 4 pixel image. So it's a toy example. So if I convolve this image with this filter with a stride of 2, this is the output. So how does that work? Well, I take these guys, I superimpose it on over here. So that's a 1 times 6 plus a 1 times 3 plus a negative 1 times 4 plus a negative 1 times 2, and I get 3. And then I go skip over 2, and I do the same operation over here, and I get 0. Then I jump down over here, and I do the same operation over here, and I get 1. And I skip over 2, and I do the same operation over here, and I get a 2. All right, that's cool. That's convolution. Nothing exciting so far. How would CUDA do something like that? You know, this seems pretty complicated, you know, geez, especially when you have real huge images and stuff like that. So CUDA says, all right, let's bite this off into, you know, little nuggets which I can handle. So the first thing it's going to do is it's going to vectorize the image using an IM2CAL operation. So this is just an alternate representation of the image. And then what it's going to do is it's going to take this alternate representation, which we have, I just copied it over here, and then I'm going to reshape the filter, and then I do a standard matrix multiply. And this is the output you get. I do one more final reshape, holy cow, and I get the exact same answer. And so what does this mean? This means I can do a convolution operation as long as I can do matrix reshaping and matrix multiply. So in the low levels, say of CUDA, it's super, super fast at doing matrix multiplies, and it's super, super fast at doing reshaping of matrices. And that's all it needs to do if it's going to be super, super fast at doing convolution operations. All right, so let's go back to the graph itself. Somehow we got to take a toy graph like this over here, and we need to represent it in the computer memory. How are we going to do that? Well, we're going to use something which we call the adjacency matrix. And so the adjacency matrix talks about the connections from one vertex to another vertex. And so there's various connections over here. And this particular adjacency matrix describes the purple, actually the purple incoming connections. So for example, this particular node, this blue node, has got 2 incoming purple connections from orange and gray, This guy over here, it doesn't have any purple incoming connections. The orange doesn't have any incoming purple connections. And then the gray, ooh, it does have one from the green. It's got one coming from the green. So this adjacency matrix over here is a way of representing all these purple connections. And you could do the same thing for the orange incoming connections. And by the way, these things don't need to be zeros or ones, binaries. They could be floating point numbers to represent, say, if it's a social network, some of my friends' connections are very strong. You know, they could be close to 1, and some are very weak. They could be close to 0, and everywhere in between. All right. And then the other things we need to store is the vertices themselves. So this particular graph can be stored in the computer memory using the 2 adjacency matrices and the vertex vector that you see over here. And so the idea is that this can be arbitrary. We can have as many of these adjacency matrices as I want. Let's say if it's going back to the social connection, some connection defined by likes or dislikes in articles. Some may be, where you live in a country. Some connections may be, earnings, how much do you make, and so on. And similarly, we can have many different layers of vertices over here. Okay, so let's see if we can do a convolution operation on a graph. Okay, so now we can represent this graph in memory, but how do we do a convolution operation? So for example, okay, so this is a toy example. Let's do a toy convolution. If I pose this to a student, I said, taking this graph, convolve it with this filter, what do you get? Oh, geez, and a lot of eyes are rolling in their heads right now. It's not an easy thing to do. But first of all, let's translate this to English. And what does this say? It says, okay, replace each vertex with 2 times itself plus sign, 1 times the purple incoming connections minus 1 times the incoming orange connections. Does that kind of make sense? So I just replaced this filter with like sentence in English, what it means. All right, say if we can handle that. The problem is that, okay, wait a minute. This filter is the same as that filter is the same as that filter. Darn it, these graphs, there is no sense of direction in the graph. So this is yet another problem. Okay, but we can handle that. So let me cut you to the chase. I'll give you the answer. So if I convolve this graph with this filter, this is the answer that you get. And you're like, Ray, I don't know about that. Okay, but wait a minute. What did we say? How did we do this? Where does this 2.9 come from? It said replace this vertex with 2 times itself, so 2 times 0.2 plus 1 times the incoming purple connections, and there's 2 of them. There's a 0.7 or a 1.8 or 2.5 minus 1 times incoming orange. There are no incoming orange, so it's 0. So 0.4 and 2.5 is 2.9. And you can do the same operation for the other vertices over here. Okay, so it can be done. Now, here's what the graph CNN said. Okay, so it took us a while to figure out, geez, what the hell, how does that really work? How can we do that? Let's go back to the CUDA. How would CUDA do something like this? Well, okay. Oh, and by the way, we want to learn many of these filters. Just like in a CNN, you want to learn many 3x3s, 5x5s, what have you filters. We want to learn many of these filters. So, okay, so how are we going to do this? So this is the toy graph. This is its representation. This is the filter, and we want to get this answer when we convolve this toy graph with that filter. So here's how you do it. Well, first thing we're going to do is we're going to pre-compute our A times V matrices. So for example, first of all, we'll just take the vectors. I just copy paste it, put it over here. This is just purple A times V. You get this vector over here. If you take a 4x4 times a 4x1, you get a 4x1 over here. This guy over here is just the orange 4x4 times a 4x1 over here, and you get a 4x1 vector. And you say, why did I do that? Hang on a second, okay? So we just did some pre-computing. Now what we'll do is we'll take our filter, and we're doing a reshape on that. And now we're going to do a regular matrix multiply of our pre-computed vector with adjacent matrix with our filter, and we get these funky numbers over here. If I do a final reshape of these numbers, son of a B, oh my God, look at that, 2.9 matches 2.9, 2.4 matches 2.4, 1.2 and 4. I just got the right answer. And these are those, I don't know if there's any students in the audience, I'm sure there are, but these are the equations we put into paper. And you look at these equations and say, holy crap, look how complicated these guys must be really smart. No, look how simple it is. It doesn't get any simpler than this. Sometimes you need these equations because math is a universal language, but of course you gotta make it look like you're smart a little bit. But no, it's just very simple matrix operations. And this is all it takes to do a graph convolution. And of course, remember, we're gonna learn families of these things. And you say, well, wait a minute. So how do I learn? So you're going to take the partial derivative of each one of these weights with respect to the cost function. It's the exact same thing when you're doing a multi-layer perceptron. It's the exact same thing when you're doing a convolution neural network. Now we're just doing a graph CNN. We're going to take the partial derivative of this weight with respect to a cost, partial derivative of this weight with respect to the cost, and this weight with respect to the cost. And so it just sort of falls into place. All right, and so I'm running out of time here. So I'm going to skip over. We also came up with a way of doing pooling operations. And so in a nutshell, we said, okay, we're going to take all the, I don't care how many vertices, you turn it in linear combination of all those vertices into one vertice, which we have over here. And then you repeat that, say, m times for a number of vertices that you want to have. The beauty of this technique is you're going to go from an arbitrary number of vertices to some fixed number of vertices. And then you could use a regular, say, dense layer at the end to do your final classification or regression operation. Okay, and this is just putting it all in a nutshell. Once again, look at these complicated matrices. You know how long it took us to sit there and stare at that? Is that right? And go through it and verify? Okay, but it's simple stuff. All right, so let's take a look at some results that we have over here. So we did some testing on ModelNet. So given a mesh graph of different shapes and objects, you got to classify what it is. ShapeNet says, okay, so given a point cloud of an object, you've got to label all these points as, say, the wings. This is the body of the plane. That's the tail of the plane. Or same thing for luggage. Oh, geez, I forgot what this is. I don't know. And here's a van. There's the wheels. There's the roof. There's the body. And then we also did it on Shrek. And Shrek is cool because it uses deformable shapes. And so that's a lot harder. In this case, it's even hard to tell what this is, but this is a picture of Mickey Mouse. And so, you know, Mickey Mouse in this case is looking like this, but there's other ones when Mickey Mouse is doing other things. So this is the category mouse. So if you take a look, so using those techniques, so really this is the latest version of GraphCNN, which is, this data actually isn't published yet. We're hoping, we got our fingers crossed, but we'll see what happens. But using this particular method, you know, we're getting either state-of-the-art or very close to state-of-the-art on all these different data sets that we tried on. And we just tested to the real flexibleness that you can get from something like this. Then we also said, hey, what else can we do with this thing? It's cool to do it on something like, you know, ShapeNet or ModelNet, we are doing point clouds, but can I use this into some, like maybe scientific discovery for engineers? Right now, when you say you go in your car and drive to work or something like that, for those of you who are doing that, you know, the aerodynamics of that vehicle, you know, it literally took thousands of engineer hours to come up with that. And most of that time was the computer sitting there crunching on those numbers, you know, doing the very detailed computation of fluid dynamics. So what we did was we said, here's what we're going to do. We're going to take these random shapes, and we had several hundred of these random shapes, and each one of those we put into one of those very slow, painstaking computational fluid dynamic computations. And then what we said is, oh, okay, so we're going to use this as training data such that when we get a new random shape, say like a car, this is the actual pressure and this is the actual velocity that you get from that. But instead of taking, say, a day or two to do these computations, this can take a second, maybe 2 seconds, depending on how complicated the car is. So it's much, much faster. And so we compared our method versus lots of the competition, and I guess I wouldn't be showing these if it weren't better. But so we have the predicted pressure, the predicted velocity of various different methods over here. And then we have the delta between the predicted pressure and the predicted velocity, and the ground truth and the predicted for each of those. And if you did a good job over here, you'd like to see a lot of green is what you want to see. So the ones that are a lot of green, they're doing really good. When you see other colors like the reds and the oranges, oh geez, that's bad. And so once again, that looks pretty good. And then just as, well, maybe we've been working on it for about a year now. We teamed up with Argonne National Laboratories in Chicago to do some high energy particle physics estimations of things like electrons and jets, and try to characterize what's going on in this high energy particle physics. And so we're just showing some results of the different techniques that we've used over here. Once again, of course, getting state-of-the-art results, and many, many other applications we've done. So in conclusion, I've tackled 3 different were presented about 3 different problems. You know, I still say neural networks are great and they're so awesome and we're so lucky. And I talked about 3 of the weaknesses, and believe me, there are more weaknesses. But the first one is that, hey, if you're going to use this thing, a neural network, in say some vehicle where maybe there's a life and death decision, or for a doctor where they're making a diagnosis, sometimes when you're giving garbage input, you don't want to tell it that you have some sort of cancerous disease or something. You want to say, hey, you just gave me, you know, a picture of a panda. That has nothing to do. You just gave me garbage. The other thing is the lots of training data. So we found that the stage-wise learning is a very powerful concept. And then the last thing is the issue that most of the world's problems don't occur on these fixed gridded structures. So when you have problems, say like protein samples or something like that, just use graph CNN, and you could use a very similar convolutional network as if it were a grid structure. Okay, so thank you. That was my last slide.
Thanks, Ray. You're ahead of time.
Good.
I think we have one question from one of the students. In your transfer learning with language, with the Seneca language, when did you know to stop the training on the current data set and switch to the new data set for English to augmented and augmented to natural? I think it's more like, what was the break point?
Yeah, so I think that's relevant with this slide over here. So first of all, you know, we do the transfer learning. You could ask the same question. How do you know when to stop? You know, when is it done with English? So we use early stopping criteria. So in other words, you keep on taking a look at your learning progress. And if it hasn't learned anything in the past 10 or 20 iterations, then you're done learning. And so what we would do is we would use early stopping initially, do the transfer learning, heavy data augmentation, keep on learning until it stops making any progress, but let it go for as long as it wants. And then the same thing in the fine tuning, as long as it's making progress. And in particular, so we test the train and the validation. In particular, we care about the validation. We want to make sure it's making good progress on the validation set.
Okay. Other questions? We are open to questions from students. I think there is another one. What could be some good self-supervised pre-training approaches for speech, rather broad, in a broad sense, I guess?
Well, first of all, let me answer that. I'm going to cheat initially. So speech, you're kind of lucky. You got so many ways of representing it. You can represent it as images or just vectors of time slices. So self-supervision is such a powerful concept. And so for those of you who don't know, self-supervision is another way of pre-learning the weights of a neural network. And by the way, if you're going to do self-supervision, we always start with transfer learning, you know, if you can. All right. 85 to 90% of the time, it's a good idea to do transfer learning first, then you do self-supervision. And in the self-supervision, we do tests. Let's see, we've done many, many tests in self-supervision. Some of the more promising ones are try to predict the future. So given the prior, say, 5 time slices, try to predict the next time slice. And then we mixed it up just like the skipgrams did. This is very small here, but this is a 3, so I'm using this as an example. Try to predict the 3 given some random guess time slice before and or some random time guess, some random actual in the future. So use the future to try to predict a 3 or use the past to try to predict a 3. And those are the ones which gave us the best results.
Okay, thank you. I think the next question was more about the graph CNN, right?
Okay.
The pooling example, why do you use only 2 colors for the adjacency matrix? I'm guessing that's more of an example.
Yeah, so I'm only using 2 colors here because I just wanted to show that it could be more than one type of connection. For example, if these are cities, and maybe this is the temperature. So the vertices maybe is the temperature of the cities. Well, the temperature of New York is somewhat related to Los Angeles and Chicago and, you know, Orlando, Florida and stuff like that. But some of these connections may be wind speed. The purple could be wind speed. The orange could be pressure. I'm not a meteorologist, so please ignore that. But the point is that you have many things which would affect the temperature. And oh, maybe you want to predict more than temperature. What other types of connections? Maybe some of these things are distance and the trade wind things that I talked about. But maybe you want to predict the humidity too. So there could be many levels of vertices. You don't just need one vertice. You can have more than one level of vertice. But it was just an example. So you would say there's, n of these adjacency matrices.
There are some, I think, students who are just entering into the field and have some questions relevant to the material or references that would be ideal for someone who is starting off in the field, I think. I know you have a lot of experience with teaching foundations, so they were asking if there are any recommendations for.
Well, first of all, school and college is awesome, there's no question. Obviously, take the classes at your university that do machine learning and deep learning. But if you just stop there, you're kidding yourself. First of all, this is a flattened world. There's a lot of competition. And the rest of the world is hoping you're only going to do the bare minimum to pass your classes. Okay? So what do you need to do? Two things. One, you need to go to the online. You need to do the Udacities and the Coursera's and the edX's of the world. And you need to take those courses too. You don't have to finish them complete to end. If you're a noob and you're just starting in machine learning, okay, you got to take Andrew Ng's Coursera course on machine learning. I mean, that is by far the most popular. I know over 1 million people have taken it so far. It may have hit the 2 million mark, I'm not sure. But so Andrew Ng, NG, he's my hero, one of my heroes. He's great. He's great at explaining concepts. He'll give you a strong foundation for machine learning. And then what do you do from there? Okay, you can either take more machine learning courses if that's not familiar, or build upon the areas that of interest to you. For example, if you like natural language processing, there's entire courses, free online courses on natural language processing. Or if you like medical imaging, free online courses. Even NVIDIA has got these short free courses. There's so many. And so the point being is, okay, so you have to take the classes at school, you got to do these online classes, and then you need to practice, okay? You need to muck around. You have to play and do your own experimentations. And if you want to get a good job, say at the Google or Microsoft or something like that, you got to have a Git page, and your Git page has got to have your projects on there. So they see that you're a hacker, you're a coder, and that you live, eat, and breathe technology, and that's what they're looking for. It's got to sort of like ooze out of you that you love this stuff for them to hire you.
Thanks, Ray. You couldn't have said that any better. There are a few more questions about the model complexity versus accuracy. How is the decision made so generalizability is maintained across data sets?
So was this with the graph, or which was this referring to?
I think it's more in generic. I don't think it was about the graph CNN, but you could shed light more based on the graph CNN.
Boy, I mean, what a good question. It's so good, I don't even have an answer. It's so good that this is still a gut feel. It's kind of like, hey, which architecture should I start with? And then how do I modify it for this particular problem? Damn, you just got to say, well, I've seen somebody else publish something, this model complexity. I always say, first of all, initially you got to get the highest accuracy that you can. You got to start there. If you can't get the high accuracy, you're not going to get the publications, and you're not going to get people's attention. Once you get the high accuracy, then you start mucking around. And then you say, well, what else can I do to shrink the model or reduce the number of multiplies or adds and maintain that accuracy as much as possible? But I mean, it's too tough of a question for me to answer. Matter of fact, we were working with well, I'll just say it's a proprietary customer for getting very lightweight neural networks. So they were trying to implement this on chips that they were building. And the point being is that, what we're seeing here with, hundreds of millions of weights, screw that. Okay, well, how about just 1 million weights? Screw that. Well, how about 1,000 weights? Ray, are you kidding me? This is, how about a couple of hundred weights? And this is where they're at. And it's like, oh my God. So it really is very application dependent. Efficient Net is a great paper, and then there was a follow-on Efficient Det, DET. Both of those are great papers. In there, in the background sections, you'll see many discussions about lightweight, efficient networks similar to theirs, and I think you'll enjoy that reading.
Thanks, Ray. The next question is from Feng. He's asking, in the first part of your presentation, I think this is more relevant to uncertainty, on around slide 18. Do you need training labels for the model to tell whether the image is related or not?
Yeah, so the good news is that you have a data set. Let's say you had 100 classes you were trying to predict. So that means you have 100 classes of real data. That's one label. All the rest of the images in the world, an infinite number of them, is the other class. So yeah, so you do need to label those things, but there is no shortage of data when it comes to collecting those.
Okay, thank you. I think there was one more question I might have missed earlier. I think this was more fundamental question about overfitting. I think what is overfitting and how it can be avoided?
Well, first of all, you always want to do overfitting. So overfitting means that your model is doing such a good job, it's almost perfectly mimicking the training data set. Now, in machine learning, if you make a model which does such a good job with the training set, oftentimes it won't do such a good job on samples it's never seen before. And creating a model, I don't care if it's a neural network or support vector machine or a classification regression tree, the key in machine learning is to making it work well on these unforeseen samples. If your model could generalize those unforeseen samples, then you've learned something. You're not just memorizing your input. However, in deep learning, it's such a complicated thing. I always tell my students, first, I want you to be able to prove that you can overfit to your data. And then we play tricks, for example, dropout or regularization or batch norm or what have to reduce the overfitting and making it generalize better to the sets. But first overfit when you're doing something new, which you've never tried before, and then make it generalize well to unforeseen samples.
Okay, sorry for jumping around. I think the next question was more relevant to uncertainty again. This was based on the neural network that was just used for uncertainty. I hope that non-classified becomes part of the validation process for all the neural networks. I see most do not perform this. So do you see this becoming the norm in validation of these neural networks?
Well, it's not as of yet. I think it's a great idea, and I hope it does become the norm. Yeah, that always should be that extra class, which means it's the unknown class. ImageNet's so famous. It's 1,000 classes. I always say there should be 1,001 classes. In other words, that sample you gave it is one of those 1,000 classes, or it's none of them. And we really need that none of them. And I think that's what this question is going towards. And so you're preaching to the choir. It's a great idea. It's just not very commonly done.
Okay, exactly. Thanks. Keith says thank you. So I think we're at almost the top of the hour. I had a lot of questions, and I'm sure there are others who have a lot of questions. Probably feel free to follow up with Dr. Ptucha. He has given his email ID earlier in the presentation. But thank you so much, Ray, for doing this, and very insightful on some of the challenges deep neural networks are facing and how we could address some of them.
Great. Nice to meet all of you, and take care.
Thank you.
All right, bye-bye.
Bye.